Today we are moving on to nonlinear constrained optimization. Okay, last time we talked about linear constraint optimization, and I introduced you the linear programming, and today it's something different. So it's getting more and more complicated. And before I introduce you a method, there's an important check. It's called the KKT condition. So why the name KKT? Basically, a combination of three researchers' name. So Korosh, Kuhn, and Tucker. Okay, so it's a very famous so-called the KKT condition. If you Google for it, there's tons of information in KKT condition. So what is it? It's one way to check whether your solution is optimal. So it's a check for optimal solutions. But only good for local minima. So if you are talking about super nonlinear functions with concave regions, multiple minimum points, KKT condition also cannot handle global optimal. Okay? Now, let's take a look at one thing. Okay. So, last time we already introduced how you can introduce slack variables to convert inequality constraints to equality constraints. So actually, all kinds of problems can be reduced to a equality constraint format, right? So last time, if you have a general problem like this, you can put an I here, so there could be tons of inequality constraints, and you can put another I here, and they are equality constraints, and let the index be, for example, m plus 1 to capital M, something like that. Now n plus m. So basically m of them, right? So in total, you have n plus m of constraints. So in fact, you can convert these into equality constraints by introducing slack variables. You can call them S. And actually, in order to make sure they are positive right here, sometimes we just put a square right here. It's a trick so that your slack variable is positive. Right? Now you have, again, n plus m constraints, and they are all equality constraints. But by doing so, you are introducing n slack variables, S1 to Sn. Okay? So in general, actually, you are dealing with a bunch of equality constraints. You can think of a general optimization problem is like this. Okay, when you are doing that, let's take a look at a particular example, a 2D example. So let's take a look at a 2D example. If I make a drawing of the functions then let's focus on a objective function. I'm going to draw the contour. So let's say the function is having a contour like this. Okay, and here is the minimum, location of the minimum. And every curve is representing a level of the same function value. And as this one goes bigger and bigger, function value is larger and larger. So the location with the star is the location with the lowest function value. Okay, so that's what we usually do. We are looking for the minimum point. Okay? And let's say we have a equality constraint, just a random function like this. So this is your h of x equals to 0. So in this particular example, we can just eyeball where the solution is. It's somewhere here. Right? Why is that? Because you can try to draw another objective function contour right between two existing ones, somewhere here. And I intentionally draw the particular contour that is passing through the red point. Right here, you realize this dash contour of the objective function. Basically, this is f contour, is tangent to the red contour, that curve, and having an intersection point at the red dot, right? So think about it. If you try to move the red dot somewhere else, I'll give you some examples. If I move the red dot here, then I'm going to violate the constraint. That's not a solution. It's not on the red curve. If I find another one here, not satisfying. If I find this one, yes, that green point, the third one, is on the red curve. However, the function value is larger. So at this point, you realize there's no other point that is better than the red point. The only point that is on the red curve, which is the equality constraint, and also having the lowest function value, is the red point. Okay? Now, if you try to draw the gradient of both functions, you will realize this is the gradient of f. And it's going to be perpendicular to the objective function contour. And it's going outward. Think about it. You increase your x, your function value increases. So the vector direction should be going outward. Okay? So why do we always move toward the negative gradient direction? Because that's the direction that makes the function value lower. So the positive gradient direction is going outward. Okay? And if I make a drawing of the gradient of the h function, it could be somewhere right here, also perpendicular to the red curve. It also could be the other way, but it's on the same line, same perpendicular line. It's either going on the right-hand side or the left-hand side, because it really depends on which function you are dealing with. It could be either way. Okay? So what does this tells us? This is telling us the gradient of the objective function is having the basically parallel to the gradient of h at the optimal solution. Parallel, okay? So, if you have another constraint, what's gonna happen? So let me see if I make another drawing. Okay, maybe I make another drawing so you won't be confused. Right here I can copy, but only if you are doing the same thing on an iPad, then you can make a copy. So let's say I have another constraint. So maybe something like this. So this is like a H1 and this is like a H2. Okay? In this case, your solution can only be on the intersection. Because you are going, if you want to satisfy two intersecting equality constraints in this 2D problem, that's the only solution. Okay? So I'm going to erase these. Because they are no longer the solution in this particular example. Okay, but at this new position, I'm also going to draw the contour again, and it's going to be like this. And I'm going to draw the gradient of all three functions. So maybe the gradient f is right here, and gradient of the red one is gonna be perpendicular like this, and the green one could be something like this. Okay. So now they are not parallel to each other. However, it's possible you can have this linear combination. Like a lambda 1 gradient of h1 plus lambda 2 gradient of h2. It's possible. You can find a linear combination. Okay? So what does the top one tells us? Basically, gradient f equals to lambda of times gradient h. That means parallel, right? Lambda can be any value, can be positive or negative. Okay? And over here, if you have multiple constraints, you definitely can find combinations of these. So if you can do that, you can, so right at the optimal solution, at the optimal, you definitely can satisfy the following equation. You definitely can satisfy it. Okay? So this lambda is called the Lagrangian multiplier. Okay, Lagrangian multiplier. And there's something called Lagrangian. Okay? So in optimization, when people talk about Lagrangian, people are talking about formulating this equation. So this equation is called this equation is called Lagrangian. Equation. For the original problem. For the original problem. So you can rewrite the original problem and then form this Lagrangian equation. And you hope, because you know when this goes to 0, that's where your, oh, sorry, this is not the Lagrangian. The Lagrangian is the other one. So I'm sorry, I need to get rid of this again. Sorry, I made a mistake. Let me tell you what is Lagrangian. So Lagrangian some people directly use an L. They write it like this. This is like a Lagrangian formulation or Lagrangian equation. And what people are doing is they can do minimize Lagrangian without constraints anymore. So this is like a unconstrained optimization. Okay? Why is it working? Because for unconstrained optimization, how do we find our solution? We are looking for gradient Lagrangian equals to 0. This gives us the optimal, right? So what does gradient of Lagrangian equals to 0 looks like? Here. This is basically partial Lagrangian and partial x. For, of course, all of the x, if you have j's, many of them. All the terms with respect to x can be combined to the upper equation. However, since we formulate so-called Lagrangian, we introduce Lagrangian multiplier. So actually, when you are handling this unconstrained optimization, what are the variables? All the x and all the lambda. The newly introduced lambdas, they are also variables. So in fact, you also need to make sure how many lambdas, i's of them. This is 0 as well. So gradient lambda equals to 0 includes two parts. One part is partial derivative with respect to all the x, and the other part is partial derivative with respect to all the lambdas. They all needs to be 0. But what happened to the bottom one? If you take a look at the Lagrangian equation, this is basically the result of this equation, basically hi equals to 0. Did you notice? So if you do that, go from here. If you take partial derivative with respect to lambda I, what ends up with is hi equals to 0. And when you do that, basically this is the same equation you had before introduction of Lagrangian. So this is also indicating you are doing the right thing. If you reformulate the problem, converting the original constraint optimization into this new equation, new formulation, without constraint, where you move your h into the objective function. How are you sure this is still equivalent to the original problem? This is the proof. By reformulating Lagrangian in such a way where you have a pre-multiplier of lambda in front of the equality constraint and sum them up with f to form this Lagrangian and minimize it. So the partial Lagrangian, partial lambda equals to 0 gives you the original equation. So this is telling you, okay, by doing so, you are doing the right thing. Okay? Let's see. Now, if we can do that, then we can actually go back and take a look at this particular problem. Oh, by the way, any questions? Are you guys okay? Any questions so far? Okay, I hope I'm slow enough. So now I would like to talk about this one. Okay? Because earlier I mentioned we can rewrite everything into this equality format. But we never directly handle the inequality one. So let's just use the exact same concept on top of this original form with the inequality constraints, with all the g's. Let's take a look what's gonna happen. So in this particular case, we now are dealing with the equality constraints of these and these with the introduction of slack variables. They are slack variables. Okay? Now let's apply the Lagrangian. Okay? So Lagrangian is gonna be, now we will have a bunch of x, a bunch of s, and we will have a bunch of Lagrangian multiplier. So I will use lambda and mu, a bunch of them. Okay? So the first one is gonna be this. And then I will have introductions of lambdas. How many of them? I of them. Hi, like this. For the index, so this goes from n plus 1 to n plus m. if I follow the format I mentioned on the top. Okay, so basically m of them, right? So yeah. And also, I will put a mu here. And this time I am putting g of I x plus s of I. Okay. For I, this goes from 1 to n. Okay? And this is not 0 yet. Okay? This is the equation. But we are looking for this, the gradient of L equals to 0, right? So let's take a look at the partial derivative of lambda of Lagrangian with respect to xj. Okay, so let me remind you about the index. So x is like x1 to xj, and how many of them? Let's use a small case n. Okay, so small s will be s1 should be having the same amount. So s same index I s capitalize n, right? And for the lambda, it's for the h, so it's gonna be lambda n plus 1 lambda I lambda n plus m. Okay, and how about mu? Mu would be mu1 mu I mu n. Okay, so when you are deriving something, make sure you keep these in mind. So now I'm handling partial derivative with respect to xj. So let's do it. So it's gonna be like this, right? Plus here I have lambda has nothing to do with x. Here I will have relationship with x. So a partial derivative with respect to xj. And then mu I here, partial g, here's I, gi, and xj, right? How about s? You don't have s anymore. So you can get rid of these. Because s has nothing to do with x. S is select variable. Okay? Right? So, what else? We have many variables. We need to do partial derivative with respect to s as well. How many s? Use the index of I, right? So what is related to s? Only the last term in Lagrangian. So at the end, you will have 2 times summation mu I and si. This must be 0. Right? Correct? Okay, how about the partial derivative with respect to lambda I? Same as what happened before, is gonna be hi, all the hi, but yes, only hi. So sorry about the above. There's no summation sign here. Because we are only doing partial derivative with respect to the ith s. So no summation. Only the ith one. The rest will be becoming 0. Right? Only the ith one. Okay? And this will be hi equals to 0. Correct? Yes. If you do the same thing for mu I, what you will get is gi plus si squared equals to 0. Okay? So from here you can see this is same as original format. The same as original problem. Okay? If I call this, if I call these, this objective function, this constraint, let me change the color to highlight what I mean. About these subject to these, of course, this number of equation, and these. Okay? If I call all these the original problem. Okay? So you realize after this partial derivative, you end up with same equation with the original problem. Okay? Also, this equation, same. Okay? Which is nice. Which means you still need to satisfy the original constraints. But this time, when you introduce slack variables into the inequality constraints, and you directly format it, you don't combine G with H. You don't do this. Earlier, I was doing this. I just combine them into a bigger H. So I never talk about the existence of slack variables. But this time, we directly handle the G plus S squared term. And we realize that will introduce a new equation that we need to satisfy. So what are the equations we need to satisfy? This one. And also this one. You can forget about 2. That doesn't matter, right? So for constraint optimization, they can be nonlinear. For nonlinear constraint optimization, at the optimal solution, if it is, sorry, there's a typo here. No typo. If the partial L partial X equals to 0, and also all the mu times S equals to 0, it could be the optimal. It could be the optimal. But you realize one thing. There are no rules about the mu. Actually, lambda. There are no rules about lambda. So, what's happening? Okay? And we are going to talk about, let me see. We are going to talk about, we will talk about. Sorry, forget what I said. It's actually no rules about lambda, but I'm trying to tell you. We don't want to handle slack variables. That's what I mean. Okay, so this is not a how should I say not a rule you want to follow. Why? Because you need to evaluate your slack variable. Because in the real original problem, the very real original problem, there's not yet introduction of slack variables. Okay, so we introduce slack variables, so we can analyze those equations by the idea of Lagrangian. But now you end up with a rule mu times s must be 0, but then you must introduce s, right? You don't want to handle s. Okay, because of this reason, that's figure out a way and then see what we can do with the slack variable. Okay, so in order to replace mu s equals to 0, we need a bunch of analysis so that we can replace it by several equations. So let's see how we can do it. Okay, so go back to this particular equation, particular drawing. Let me copy this one. Copy. Okay. Okay, so over here, I'm gonna get rid of the unnecessary things. Okay, so let's say this is the optimal, right? This is your optimal solution, x star. In fact, yeah, that's the optimal. And okay, this time we are not going to use h as a function. We are going to replace the whole thing by basically different scenario. This time, this is a g function, okay? So on this particular curve, it's g equals to 0, and above it, it's going to be g negative. Underneath it, it's going to be g positive. So what do we usually want? We want, we add, where is your feasible space? It's actually on this curve, and also everything above. So this is your feasible space. Because this is where your g is smaller than or equals to 0. Anything on the left-hand side of this space is having g positive, which is bad, okay? And if you evaluate the gradient of g, gradient points to the direction where the function value increases. So the g gradient in fact, it's pointing at the infeasible space. So this is the right drawing. Now, let's think about a new idea, which is so-called the small perturbation. So if I have a small change, okay, and we call this a D vector, okay. So what is a D vector? D vector is a very small perturbation, basically small change from your optimal. If this is happening, let's see how this D is having a relationship with everything that we know and how it's gonna affect your solution. So if you take a very close zoom in near the optimal solution, actually the constraint is looking like a straight line, right? This is your G. Actually, let's talk about F. Even for the F, this is your F contour, okay? When you are very close, it's like a straight line. And this is your optimal solution, okay? And your gradient F is perpendicular to your F contour, okay? And your D could be anywhere, any direction, okay? So there would be an angle between your gradient F and also the small perturbation. So if I want to keep this solution to be optimal, if I want to keep the solution to be optimal, okay? That means I don't want the function value to be lower, right? That means larger. Function value cannot be larger, right? If that's the idea, we are saying we are trying to keeping the optimality of the solution. We're trying to keep the optimality. Okay? So when this is happening, what do? We actually want let me see. Function value if it's 90 degree, if the angle is 90 degree, then the dot product between them equals to 0. So if it's smaller than 90 degree, the dot product is positive. If it's larger than 90 degree, it's going to be negative, right? Yes, negative. But going this way, function value increases. So the concept. Let me clear my mind and then see what would be the proper way to talk about this. Can we positive goes this way. positive. This one is positive. So G goes this way, and positive. Okay, I think I cannot explain in this way. I have to explain with the existence of constraint. I cannot just talk about this just with the object function alone. So my mistake. This is also the G contour, right? If you are so close, contour. The F contour and the G contour, they are just straight lines, okay? And let's draw the G gradient. G gradient goes down, okay? So if this is happening, then I should not say this. Sorry if you already write it down, okay? So I'm looking for a solution that is also optimal and feasible. So because of the combination of optimality and feasibility, the small perturbation cannot be anywhere. Small change cannot be anywhere. So if the small change is like this, here's your gradient, here's your solution, and here's your gradient of G. If your small change is along this contour, it's still okay, because it's very small change, but it's okay. Your objective function value didn't change, and you still satisfy your constraint. So D dot product with F equals to 0, and D dot product with gradient of G equals to 0 at this situation. However, on the left-hand side, left upper corner, here, D dot product with gradient of F now is positive, and D dot product with gradient G is negative. Okay, this situation is also okay because your solution remains feasible, and if the perturbation D is very small, your function value didn't change too much. Okay? So by these, everything seems okay. However, you don't want the third case. You don't want this is happening. You don't want this, because this small perturbation goes into the infeasible space. It's going to violate the constraint function. So you don't want D dot gradient F to be negative, D dot G to be positive. You don't want these. So overall, you can accept this to be positive or 0, and this one negative or 0. Okay? So now, if we apply this, but how about the equality constraints? similar concept applied to equality constraint. You can only accept 0. Why is that? If the constraint is an equality constraint, you can accept here. So this is good for equality constraint. But for the left upper corner, it's not good for equality constraint because it's already out of the dashed line. So the function value of h changes. It's not satisfied. So think about optimization. You always need to think about optimality and feasibility. Okay? And that's why we end up with these 3 rules. Now let's apply the rules on top of this equation, the first partial derivative for Lagrangian. Let's do that. So let's do a d pre-multiply with partial lambda partial xj. If you do that, you end up with dot product. Actually, I'm gonna just write it in this way. Sorry. The gradient, but this time only x lambda. All of the x part. So this is going to be d pre-multiply lambda f plus d dot product with all the h plus and also the actually put the summation on the outside. I of them, right? Lambda I d dot product or the hi, right? Then also I use I, mu I, but the index I changes. Mu I d dot product and all the gi's. And we want this to be 0, right? So now take a look. This must be positive or 0, right? And this must be 0. And this must be smaller than or 0. Okay? So what does that tell us? Lambda can be positive or negative because it's multiplying with 0. So we don't even care about the sign of all the lambdas. However, all the mu's can only be positive or 0. Why is that? If one of the mu is negative and it's multiplying with another negative term, then it's becoming positive. But d dot gradient f is also positive. So it would be possible this equation is not 0. So only possible way this equation is valid, all the mu's must be positive or 0. Okay, so that gives us a new rule. Mu I must be positive or 0. Okay, that's a new rule. So I'm going to call this one equation 1, this one equation 2, and this one equation 3. Okay? Now, we haven't talked about equation 2. So let's observe equation 2. Okay? equation 2 is mu I Si equals to 0. Mu I Si equals to 0. Okay? Now, remember, we already know Gi plus Si squared equals to 0. So what are the possible situations for S? S can be non-zero or S could be 0, right? And these two scenarios is going to affect what's happening for equation 2. So let's take a look. When S is not 0, mu must be 0. Otherwise, equation 2 won't be valid. When S is 0, what's going to happen? G has to be 0 on the left-hand side, right? So, because of this equation 2, and because of how the original equation looks like, the only situation that you can think of about mu and S are here. So it's either mu equals to 0 or G equals to 0. So combining all the possible situations, we have this new rule, mu I Gi equals to 0. And we are calling this equation 4. If mu I Gi equals to 0, that covers all the possible scenarios about equation 2. So we no longer need to talk about S anymore. Okay? And how about mu? We have equation 3. Mu must be positive. How about lambda? Lambda can be anything. So lambda has no rules. So overall, let's combine all the rules together and look at the very, very original problem. So KKT condition. On top of the very original problem. Okay, and I was using something like this, so I will stick with it in this times notes. Okay, so the conditions are: first, partial derivative of x plus summation lambda I hi xj plus all the mu I gi xj equals to 0, right? And the index goes from 1 to n. This goes from n plus 1 to n plus m. Okay, if that would be the index that I'm using, and this is for j goes from 1 to small n. Okay, second rule. Mu I gi equals to 0, and index of I is I goes from 1 to n. Okay? Third rule. All the mu I must be positive. Okay? Same index. That's the complete KKT condition. If your optimal solution satisfies all three, then it should be at least the local optimal. Okay. So I need you to practice at home, because I may not have enough time to practice today. go back to any problem that you have solved, especially on the linear programming problem. Just use the last week's example. If you apply KT condition, you will realize it's satisfied. Okay? So in your exam, let me remind you how I'm gonna, is it next week? Or 2 weeks later? 2 weeks. 2 weeks. So what am I going to do next week? Let me see. Optimization. Next week, right? It's next week. Because I know I need to finish QP today, but QP won't be included in the exam. So up to this point, that's everything I want to include in the exam. Up to here. So let me tell you about next week's. Okay, because of the exam, I would like to give you more time. So please come at the original time. So 9:10 to 12:10. So you will have exactly 3 hours to handle, right? I will give you equations. So you don't need to memorize the following. But what I usually do is I will write down the equation, but I won't tell you which one, what is it for, okay? So I will give you the 1D Newton's method. So it's gonna be like x. This is Newton's method, 1D. I can give you the multi-dimensional Newton. Okay, and then I can give you the Stevie's decent, so it will be something like this, and I can give you the conjugate gradient. Conjugate gradient looks like this. I think it's current one over last one, right? Square. What else can I give you? I will give you the linear programming equation. Is gonna be this one. For linear programming, you must figure out the procedure. You need to memorize it. But this equation is hard to memorize. So I will give you that. But just that. The procedure needs to be memorized by you. And also I can give you this. If you have no idea what's going on, it doesn't help you, right? You need to figure out. So for the ratio test, I can give you this term, but this would be J. What is J? Go back and figure out. Go check the notes. Okay, and then for the KKT, should I give you the KKTs? I think I will give you in a more cleaner form. I will give you this. This is a vector form. And also mu g equals to 0. Yep. I can give you these. So those will be shown in the exam sheet. And usually I would like to test whether you understand what's going on. So I usually don't give you in the right order. So just scramble them, okay? Of course, these will be put together. These will be put together. It's too mean if I scramble these guys. These will be placed as a put as a group. These are a group, okay? If I also scramble these, you will hate me, right? But for the rest, I may just scramble, okay? Now, how many problems I may give you? I don't know yet. I haven't created a problem, but it could be something like this, like maybe solve some unconstrained minimization problem by Newton steepest descent conjugate gradient, and maybe with some maximum iteration, okay? So I won't ask you to solve like 5-6 iterations, maybe 3 times at most, probably three iteration max, okay? And I may give you random numbers, so everyone will you won't be able to cheat during the exam. And then I may ask you to solve a LP problem. It should be a simple one. And check solution with KKT. Just use KKT to confirm the solution is the optimal. Okay? And over here, I usually give you 2D problems. So I think they are 2D problems. Which means for the LP, no, not yet. For Newton, so for 2D Newton, you need to do how to do 2D inverse agent, okay? And usually it's very easy. Usually it's gonna be like some number A and B, 0 and 0 inverse, and it's actually 1 over A and 1 over B. Because that's the only kind of problem I can give you in the exam. Otherwise, the solution procedure will be very unstable. So, easy for 2D Newton. But for the LP, 2D LP, usually it's going to be having a 3 constraints. Okay? So your A matrix is gonna be you usually have two columns. One is for x1, the other one for x2, right? And you have 1, 1, 1, 0, 0, 0, 0 at the beginning. These are because of the slack variables. So it's a 3 by 5 matrix. And what's happening is for the A non-basic inverse, it's going to be a 3 by 3 matrix inverse, right? You will need, for the AB, basic. How many basic? Three basic. Yeah. So here, for the basic one, it's gonna be a 3 by 3 inverse. Do you need a 3 by 3 matrix inverse equation? Do you need it? Yes. Come on. So here, I will also give you equation for 3 by 3 matrix inverse. Okay. I'll do that. That's all. Okay, that's probably the exam is gonna look like. Okay. In today's progress. Oh, by the way, for the next week's exam, Patel, can you come at 9:10 and deliver? Thank you. Because I go to the gym, I will be late. Yeah. Now, let's move on to what I'm going to cover for the rest of the day. It's something called quadratic programming. Quadratic programming. So-called the QP, okay? Probably the most popular nonlinear optimization solver. So for QP, QP can only handle certain type of optimization problem, just like LP. So in general, you also write your problem in this way, a general form, but this one can only be quadratic. And for the constraints, they only can be linear. So quadratic means second ordered. So it's not so powerful. It only can handle linear constraints. Okay. But it's already more powerful than LP because it can handle the second order objective function. So what if your functions are having higher orders? You can always use Taylor expansion. And this is actually what happened. Later on, when we derived equations for QP, we will be using Taylor expansions to get quadratic objective functions and also linear constraints. So what does it mean? We are going to have objective functions looking like this. The G functions is going to be looking like this. H functions are looking like this. Okay. Do you know why? Do you know why in the objective function it's a x dot product h dot product x? Think about second order Taylor expansion. You have a bunch of constant terms. So basically, you have constant terms. But remember what I said in the past. Constant terms in objective function means nothing for optimization. Because no way you can vary the constant terms. They are just values, constant values. It doesn't change. That's why we ignore all the constant terms. Okay. So if you do second order Taylor expansion, you can end up with something like this. And what is C? Basically is going to be your gradient. Think about Taylor expansion. C, the position of C is actually your gradient. And we are familiar with ax minus b. It's same form as the linear programming, but this time we use it on G, the inequality. And for the equality one, we use different symbols. We use nx minus e. Okay? Now, let's start to work on these. We will be introducing a lot of new variables, so we need to keep tracking on all the variables we have. So I would like to have a variable list right here on the right hand side. Now we have x. Later on, when we introduce slack variables and a bunch of Lagrangian multipliers, they are new variables. So we will keep tracking on those. The goal is we are going to apply whatever we have learned so far, the slack variable tricks, Lagrangian tricks, and we are going to reformulate everything into linear forms. So we can solve it actually by LP. So whenever you see an equation that is already having a linear form, that is good. So this one is already good. This one is already good to go. Okay, and also we for the general problem, because we are using LP to solve it, we can only handle positive x. So this is one additional variable bound that we must satisfy. Okay? And because we would like to have smaller than or equals to sign. So let's rewrite it into negative x smaller than 0. Okay? Because we want to handle smaller than sign. Now, the first thing that we are going to apply is Lagrangian. Lagrangian. So why do we do a Lagrangian? Because of KKT. From KKT, we formulate Lagrangian. So the Lagrangian equals to f plus, so here we're going to introduce slack variables. And we are, because there are many of them. So we have this inequality. We have this one is equality. We also have this one is inequality. Okay? So we are applying Lagrangian multiplier in front of each of them. So here we use a u vector for G, and we use v vector for H, and we use a w vector for just a negative x. Okay? So here we already introduced 3 new variables, u, v, and w. They are Lagrangian multipliers. Okay. Lagrangian multipliers. Now, because of KKT, we would like gradient of L equals to 0. So we have this form. Here, directly, -1, so negative W equals to 0, correct? Because you are taking partial derivative with respect to x. So this is actually gradient of x, gradient of x. Okay? And now we can plug in whatever we had at the beginning and then see what's gonna happen. So because f is right here on the top, if we do gradient of f, we will have Haitian dot x plus c, right? And then g function, if you do gradient of x, ends up with a, capitalized A. So it will be A is a matrix, dot product with u. Okay? When you have matrix and vector, you put matrix in the front. And similarly, you will have gradient of H gives you N matrix, and the vector is V. So here, minus W. This one equals to 0. So from here, you can see a bunch of matrices multiplying with a bunch of variables, sum them up. This is a completely linear equation. So this is a very good form. We are going to draw a red box on top of it, because we like the equality ones. This is a very good one. Now, what does the second rule of KKT tell us? We want, this is basically KKT rule number 1. Now, KKT rule number 2 tells us if you have inequality ones, the Lagrangian multipliers times your inequality ones must be 0. And also, we have another one on the right-hand side, the third term, last term, W dot negative X. These two are the inequality ones. Okay? So this already implies W dot X equals to 0. So let's draw a box right here. Okay, not very good, but hold on, is it good? Yeah. It's a good one. It's someone we will be using. So let me draw a red box. Whatever good one I will draw a red box. Okay. But UG equals to 0 needs to be revisited. So what is G? G is AX minus B. So let's take a look. Let's plug in. This is AX minus B. This has to be 0. Okay? So over here you will have U vector times matrix A, which is a bunch of equations, dot X. So you have U dot X. It's a nonlinear term. It's not a linear term. So this is some equation we need to handle later on. So how do we handle it? So this is so let's keep in mind not the final form yet. they are not linear equations. So we need to go back and take a look at this one. So how about the KKT rules number 3? The Lagrangian multipliers for inequality ones must be positive. So this is positive, and this is positive. Okay, those are fine. Let me draw a red box. Those are fine. Now, from KKT, we have that particular equation, which is not the final form yet. So we need to spend some time on these. So what do? We can introduce slack variables. So now the another trick, slack variable. On top of which one? On top of G, because G is the one that is not resolved yet. So if we do that, we will be doing this. A x minus b plus a vector of s equals to 0. And this time we don't use s squared because we are going to solve this whole thing by linear programming. Linear programming can only handle linear functions. If you use s squared, it's nonlinear. So with this introduction, you need s be positive. Okay, so these two are the equations that are important. And when we do that, we will have new variable s. This is a slack variable, newly introduced. Okay. So what else have we? What else is not handled? Let me see. Yes. Let me see. Okay. So we can hold on, that's fine. We don't have rules of U because of the unresolved form, right? So in order to handle U, the Lagrangian multipliers for G, that is U is the troublesome part. So we need some equation, linear equation or equality equation that can at least handle what we have so far. So if you apply, if you do this, you dot the whole thing right here. This must be 0 as well. And you will realize it is actually having a form like this. And because what we had earlier, right here, it tells me this is 0. So at least we have a shorter form, U dot product with S equals to 0. So the unresolved equation right there can be applied down there. So the longer equation now is shrink to u dot s equals to 0. Is it a linear equation? No, it's still nonlinear because u is a vector, is a variable, s is another variable. The dot product of them is like a x squared. It's like a x times y. It's nonlinear. So this would be the troublesome part for linear programming later on. However, we still need to keep in mind this equation must be valid. Okay? What else? Every time we derive these, there's one thing that we never talk about. Actually, is the v. If you go up and see, you will see this one. This one describes the relationship between w and x. This one talk about the relationship between u and s. But how about v? No equations about v. So here we are going to see what we can do for v. So there, what is v? V is the Lagrangian multiplier for h. And remember, when we derive KKT, we never mention the rules about v. Actually, v can be anything. But if we allow v to be anything, that means v could be negative sometimes. And for linear programming, we don't allow any variable to be negative. So in order to avoid negative v, we are going to do something. We are going to define y and z. They are new variables, artificial variables. So y and z. They are just artificial variables. Okay? For this particular purpose, such that v equals to y minus z. Okay? And it's not 0. Because when the Lagrangian multiplier equals to 0, it's trivial. That means that particular constraint does not work. So only rule for v is the Lagrangian multiplier doesn't want to be 0. So what can you do for y and z? So over here, we will define y and z in such a way that they are positive. They can be any value, but they are not the same. If they are not the same, v can be either positive or negative. So there are just two positive values all the time, but not the same one. If they're the same, then v becomes 0, and that particular its partner, the equality constraints, become invalid. Okay. So this one is also a linear equation. Now actually we have all the equations. So let me collect all equations. Okay? Actually we have this particular one. We have this one. Okay? And we have this one. Another one would be the linear equation we already have at the beginning. Okay. Also, there are two. There's another. Oh, there are two nonlinear equations that we didn't resolve. This one is this one. Yep. And the other one is this one. Okay. And there are more equations that we created. What are they? They are equations that describes how those variables are positive or zero. So that's apply some markers on the ones we already collected. We collected this one, right? We also collected this one. We also collected this one. And we collected the nonlinear one. This is a nonlinear one. Okay? And if you take a look, I use a different color. How many variables we have? X, okay, positive. U, positive. W, positive. S, positive. Y and Z, positive, positive. How about V? Already replaced by Y and Z. Okay? So in fact, at the end, you will have all the variables X, U, and W, select variables Y and Z, all positive. Okay, so what can you do? These are linear equations that you must satisfy, and these are variables must be positive or zero. So it is matching the linear programming form. Okay, so let's handle these so far. So this is satisfying the LP format, right? But we are going to collect them, reorganize them in a vector and matrix form. So you can have actually a big matrix. Let me see how many. 3 of them. 4. 1, 2, 3, 4, 5, 6. Okay. There's many positions and the vectors. All the variables equals to 3 output. Okay? No, now I'm going to put everything into this. But when you put everything into the matrix and the vector form, you need to be aware that sometimes they are transposed. Is it? Which one is transposed? Oh no, they are not because they are all matrix times a vector. So you don't need to transpose any of them, I think. Yeah, you don't need to transpose. So now let's take a look at the first equation. You have a H pre-multiplier for there's a C. So C is sorry. I'm going to handle the first equation at the bottom to match my notes. So H here times X, right? There's a C. It's a vector of constants. So constant values goes to the right hand side, so negative c here. Okay. So Professor, for linear programming, you said on the right hand side, everything has to be positive, right? Yeah. So when you derive it, it's possible on the right hand side you may have negative values. So programming wise, once this is derived, some of the terms will be negative on the right hand side. Then just multiply -1 for that particular row. Okay, that's the tricky part. Okay, anyway, that's algebraically derive this, and then when you implement it in computers, it's there are small things to handle. But let's continue. So the third term is a times u. So here a times u. A times u here, right? And then n times v. But remember, v is replaced by y minus z already, so I didn't update it. So this one already y minus z actually. Okay, I didn't update it. So for y in front of it is n. For z in front of it is negative n. And for w it's -1. Actually, it's gonna be an identity matrix. Okay, because it has to be a matrix times a vector. So if you want everything, if you want to have a matrix multiplying w and ends up with negative w, so what you are multiplying is negative identity matrix. Okay, so here is basically 0 for s. There is no s in the first equation. Second equation, I'm going to put it in the first row. So a in front of x minus b goes to the right hand side, so positive b, plus s, so plus identity here. That's everything. And the third equation, n in front of x, and then negative e becomes positive e to the right hand side. The rest are just 0. Okay, so here's a huge linear programming equation. So you can solve it by linear programming. So I'm going to call this guy capitalize B. It's a matrix. I'm going to call this guy capitalize X. It's a vector. I'm going to call this guy capitalize D. Is a vector. So basically, you're trying to handle B, X equals to D. And all X positive or 0. Right? You are now handling these. However, there's no objective function, right? So there's a trick. This is what introduced. This is how I was taught, and I tried it once. It works, but so this is not the only format. So what you are going to do is you can formulate a new problem. Okay? With new artificial variables. And over here, I will handle them very carefully. I will use a different symbol. Let me see which one I didn't use. I will use C, D, E, F, G, H, I, J, K, L, M, N, O, P. I think I didn't use P. Let me define P. So let's solve a bunch of P, minimize P1 plus P2 plus PM, and then let's define this capitalize P as a vector, so basically P1 to PM. Okay, so what are they? They are additional variables. For what? For this, I will have this a B matrix X vector minus D. This is an equation I want to satisfy, but I want this to be 0. However, if you have no idea what's the variable, how are you going to satisfy it? Okay, it's like difficult to initialize the problem. Like in linear programming, you introduce Slack variables, and then you start to pick up what is basic, what is non-basic. But there's a rule for that. You need to start with a feasible solution. So why do we do whatever that we're doing right now? For LP, you need to start with a set of feasible solutions. Like earlier, we start from 0, 0. That's a feasible solution. But now, when we derive this QP, you are not even sure you have a feasible solution. What is a feasible solution? Whatever solution set of capital X satisfying capitalized B times X equals to capitalized D. You don't know what it is. So this particular minimizing P problem helps you to find a feasible solution. So you will be doing this. This one equals to 0. And also here, all the X positive and all the Y positive. Not Y, sorry, P. Here's P. All the X positive, all the P positive. So in fact, this is the LP problem we're solving. So what's the size of P? Basically, same size as the. Let me be sure. Same size of D. So length of P equals to length of D. This is how this equation is going to valid, right? So those P's are just artificial ones. And you will be, you basically solve this by LP. And remember, you will be having matrices like these. You will have a bunch of, let me see how I draw it. Here are your P's. So it's going to be like a 1, 1, 1, 1, 1, 1, 1, 1. And here's where you have your BX minus D, right? and you will have, here's your all the p's, and here's all of your sorry, it should be like you can actually move your D on the right hand side. You can move this here. So you don't really need to. You just treat all the P's, they are like select variables. You can solve this. So at the end, it's like you have a bunch of your original B, and this is your newly introduced Y, but the coefficient is like a 1, 1, 1, 1, and you have your original X, right? And this is your newly introduced P equals to the D. So you will set these as basic. This is non-basic. So this is how you can start. Because when B are non-basic, they are zeros, right? All the X part are zeros. So you just, what's your initial solution? Your initial solution is P equals to D. Because 1, 1, 1, 1 multiplying P equals to D. So your initial point is all the X equals to 0, and your P equals to D. Right? You start your linear programming from here, and then you start to solve the problem. And you have an objective function. You will be minimizing. You have something to minimize. So at the end, you will get a solution. And what's gonna happen is, at the end, your B will have some values. And the goal is all the P becomes 0. So if you keep on doing LP process, at the end, here are the 1, 1, 1, 1, here are the B part. You want these to all being part of non-basic. Right? Multiplying the, here's your X and here's your Y. Not Y, P. Equals to D, right? If this is happening, that means all the artificial P's become 0. So right here, all P now becomes 0. And rest of the variables satisfy B dot X equals to D, right? That would be a good point. That would be a good point that satisfies the rule. So this is one way for you to find solution set that satisfy Bx equals to D. So why is it important? Because this equation is derived from KKT. If you can find a solution that satisfies this equation, that could be the solution. But remember, even if you find this, there are two nonlinear equations that was not evaluated. So when you solve this minimize P problem, you need to check. Now check the nonlinear, the two nonlinear equations. If you find a set of solutions that satisfy Bx equals to D, because of LP, you are sure all the x are positive. And if you go back and check the two nonlinear equations, they also satisfy, that's the optimal. Because whatever you did ends up with satisfying all the equations you derive from KKT, that must be the solution. So what if this trick doesn't give you a solution that satisfies the nonlinear term? Then you can solve it iteratively. So that's why sometimes there's something called the sequential linear programming, SLP, or sequential quadratic programming, SQP. Okay. So it took you so long, starting from formulating these equations from KKT, but you still have two nonlinear terms, and you invent this minimize P problem so that you can find a set of solutions at least satisfy Bx equals to D. And you go back and check whether it's satisfying your nonlinear equations. If not, okay, then that's not the optimal yet. So maybe you have to solve it sequentially. So you use this new solution, not the true solution yet, to do your Taylor expansion again. Let's hope the solution you have right here is a little bit closer to the optimal. Not the optimal yet, but maybe a little bit closer. From there, do all of your Taylor expansion again, and then do the whole thing. Until one day, let's hope this procedure moves you to the optimal. Okay. And when I was a graduate student, QP was never in the exam. It's too complex. Because let's take a look. This is the original problem. Okay. When I was a student, we need to memorize this. So my graduate course exam was to derive this in the exam sheet, but never asked us to solve by hand. Why not? Because even for a 2D problem, just x1 and x2, you're going to introduce so many new variables. Slack variables of u, Lagrangian multipliers of u and w, slack variable s, artificial variable y and z. So the capitalized X contains x, u, w, s, y, and z. There are many of them. It's gonna be at least 7-dimensional problem, or maybe 10-dimensional problem. How can you solve a 10-dimensional problem in an exam? So it was never in a handwritten exam. And yeah, so when I was in USA, this is the end of learning QP. I think I tried to program it in computer in MATLAB once. It worked. It worked. So if you wish, you can try it. So how do you do SQP? The concept of SQP, I think, would be there's an original problem. You have a initial guess, right? You do Taylor expansions, and then you have general QP format, and now you can solve the P minimization problem. And then you can check the two nonlinear equations. Nonlinear equations. So if not converged yet, you of course you need to probably go back. So if I would say if it is not converged, actually even if it's converged, no matter what, you need to, because if it's satisfying, it's only the optimal of that QP problem, right? Is the solution of that based on that expansion. So you still need to do a convergence check. Let me move it like this. Convergence check. Sorry. So solution, optimal. Only if it's converged. If not converged, you should basically k equals to k plus 1 and not converged. You should do expansion at that new solution, right? And also, I think you should do this as well. This here is k equals to k plus 1. So if this is like a satisfy, this is not. So if it's not satisfying your nonlinear two nonlinear equations, is not the solution. Is not the solution for the QP format. So that's just do expansion again. Okay, so it's like you have this small loop, you keep on updating. One day you found, okay, great, I satisfy the QP and I also satisfy the nonlinear one. Now you have this loop to satisfy, because maybe not the true solution of the original problem, because whatever you do in the small loop, you are getting the optimal of the approximated problem, not the original problem, right? So you need to keep on doing it. Okay, so I think a good procedure would be something like this. Does it guarantee to find the true solution? If it's if it's a polynomial, I think it should be, and also nicely shaped. I think it should work. Okay, but nowadays we can use MATLAB and a function called fmin_count. Next time I will show you how to do fmin_count. It's a SQP based solver in MATLAB. But does it stick with SQP all the time? No. This fmin_count is quite smart. It switches from method to method when it's dealing with different scenarios. Okay, so it's probably it's a well programmed function in MATLAB. What's the trigger for switching? No one knows, right? It's a secret for them. And I did have a graduate student in the past who programmed SQP by himself in C++ when he was doing some kind of optimization in his thesis. Okay? So I don't think he followed fmin_count. He just programmed this whole thing, and I'm not sure if he did the P minimization. I'm not very sure. There are many ways to handle QP after this. This is not the only way. P minimization trick is not the only way. But deriving this equation is like a general procedure for QP. And people try different ways to solve the problem so that it's gonna satisfy this general form right here. Okay? Actually, if you do Taylor expansion of these two nonlinear equations, you can force them to become linear as well, and then solve it by a expansion version of the LP. That's also another trick, right? But I never do it. You can try if you want. Maybe there's already someone did it. But if you are making linear approximation of these two nonlinear terms, then you need to sequentially, again, every time you have Taylor expansion, you are making approximations. Then you need to iteratively check whether you are truly satisfying this original nonlinear equation. Okay, and there's always multiple layers of iteration loops, and you need to satisfy all loops, smaller loops and bigger loops, until everything satisfied. Okay, then you are sure this is the optimal. Okay, so that's it for today. Any questions? I think the QP part of the derivation is for you to learn something new, but for you to program this, it's a little tricky. Okay, if you want your final project to be related to QP, I'm happy to see it, because I know there are many researchers are working on how to solve QP. So if you like this and you want to extend different ways of handling QP, that'll be interesting. Okay. So I guess for this week, please go home and practice how to solve these. So test yourself, generate random problems, solvable problems, and then apply to my MATLAB code to see if the MATLAB code generate proper solution. Okay, MATLAB can solve it. My code can solve these. That means they can be solved by hand. Now, practice by hand. So you can generate all kinds of problems. But sometimes when you practice by random problems you generate, maybe you randomly generate something that is not solvable. That's why my MATLAB code can help you to confirm this is a solvable problem. If MATLAB can solve it, you can solve it. Okay. Any questions? So for this course, the exam is very important because we don't have homework scores, we don't have quiz scores. This is it. If you do well in this one, you probably can get a good score for the course. Because for the project, I can never give you fail. How can I say you failed the project, right? If you've completed, I can only give you a final score in the range from maybe 70 to 90 something. But it's hard for me to give you, oh, this project is 30. It's impossible, right? So you won't get a super low score in projects. But for exams, it's on you. If you are not doing well, this could fail you. Recently, not only our school, many universities around the world, not around Taiwan, is trying to see a very special issue. Professors nowadays tend to give students higher scores. They think the average is too high. Because when we give the score too high, it's hard to judge who is it's hard to judge the rank. So our school is telling us, okay, don't try to treat the student too nicely. Just give them fair scores. Okay? So I don't want to adjust your midterm exam score. I want to just give you whatever you deserve. So if at the end, the overall course score distribution is not very high, I will be happy because I'm satisfying what the school is telling us. The school now asks us, don't give everyone A. That's what the school says. Okay? But if you guys can get good scores, everyone gets A, I won't reduce your score, okay? That means I need to make my exam harder next semester. So, but if you are not doing too well in the exam, then it's not my fault, okay? I think these are not very difficult. I give you equation sheets. You just need to memorize the procedure and then solve the problem carefully. And you need to be familiar with the procedure so you have enough time to solve everything. Look at this. There could be multiple times of doing optimization and a lot of calculations. So if you are not familiar with the procedure, if you make a mistake here, maybe the rest is wrong, right? So please go back and practice. And I think if you practice enough, everyone should get good score. If everyone gets 90 above, then I don't know what to tell the school. But if everyone fail, then I don't know what. So I want nice distributions, Anyway, that's what I'm gonna say for today. Any questions? Okay, if not, good luck next week. Okay, bye-bye.